നമ്മുടെ കണ്ണൂർ എഞ്ചിനീയറിംഗ് കോളേജിൻ്റെ അലൂമിനിയുടെ ഒരു സ്ട്രെങ്തൻ ചെയ്യുക, അലൂമിനിയെ സ്ട്രെങ്തൻ ചെയ്യുക എന്നുള്ളതിൻ്റെ ഭാഗമായിട്ട് എല്ലാവരുടെയും വളരെ കോപ്പറേഷനോട് കൂടി നമ്മൾ സ്റ്റാർട്ട് ചെയ്തൊരു പ്രോഗ്രാമാണ്. ഒരുപാട് പ്രോഗ്രാമിൽ ഒന്നാണ് ഈ മന്ത്ലി ടോക്സ്. അപ്പോൾ ഈ അലൂമിനി ടോക്സ് കൊണ്ട് ഉദ്ദേശിക്കുന്നത് നമ്മുടെ അലൂമിനി മെമ്പേഴ്സ് ഒരുപാട് പേരുണ്ട്. കഴിഞ്ഞ ഇപ്പോൾ 30-ലധികം വർഷങ്ങളിലായിട്ട് ലോകത്തിൻ്റെ പല ഭാഗങ്ങളിലായിട്ട് വർക്ക് ചെയ്യുന്ന, വളരെ റിച്ച് എക്സ്പീരിയൻസ് ഗെയിൻ ചെയ്തിട്ടുള്ള ഇവരുടെ ഒക്കെ സേവനം പല പല ഇൻ്റർനാഷണൽ കമ്പനീസ് യൂട്ടിലൈസ് ചെയ്തിട്ടുണ്ട്. ആ റിച്ച് എക്സ്പീരിയൻസിൻ്റെ ഒരു ചെറിയൊരു തുള്ളിയെങ്കിലും നമ്മുടെ കോളേജിൻ്റെ അലൂമിനിയസിന് അല്ലെങ്കിൽ ഇപ്പോഴത്തെ സ്റ്റുഡൻസിന് അവർക്കൊക്കെ ഉപയോഗമാകുന്ന രീതിയിൽ ഒന്ന് സ്പ്രെഡ് ചെയ്യുക, എല്ലാവരിലും എത്തിക്കുക എന്ന ഉദ്ദേശത്തോടു കൂടി നമ്മൾ സ്റ്റാർട്ട് ചെയ്തതാണ് ഈ മന്ത്ലി അലൂമിനി ടോക്സ്. ഇതിൻ്റെ ആദ്യത്തെ സെഷൻ കഴിഞ്ഞ മാസം ജൂലൈയിൽ നമ്മൾ ഓൾറെഡി നടത്തി കഴിഞ്ഞു. അപ്പോൾ ഇനി അങ്ങോട്ടും എല്ലാ മാസവും സെക്കൻഡ് സാറ്റർഡേ 7 o'clock തന്നെ ആവണമെന്നില്ല, പക്ഷേ സെക്കൻഡ് സാറ്റർഡേ ഒരു കൺവീനിയൻറ്റ് ഡേറ്റിൽ നമുക്ക് പ്രതീക്ഷിക്കാവുന്നതാണ്. അറേഞ്ച് ചെയ്തിട്ടുണ്ട്, സ്കെഡ്യൂൾ ചെയ്തിട്ടുണ്ട്. ഒരുപാട് മെമ്പേഴ്സിൻ്റെ നമുക്ക് ഇവരൊക്കെ നമ്മളിനി വരും മാസങ്ങളിൽ സെക്കൻഡ് സാറ്റർഡേ അവരിൽ നിന്ന് അവരുടെ എക്സ്പീരിയൻസ് അല്ലെങ്കിൽ അവർക്ക് ഇഷ്ടമുള്ളൊരു സബ്ജക്റ്റ്, അവർക്ക് അവരുടെ ഹൃദയത്തിന് ചേർന്ന് നിൽക്കുന്ന ഒരു സബ്ജക്റ്റ്, അതിൽ അവരുടേതായിട്ടുള്ള രീതിയിൽ ഒരു പ്രഭാഷണം, ഒരു സെഷൻ എടുക്കുകയും അതുവഴി നമ്മുടെ പുതിയ മെമ്പേഴ്സിനും പുതിയതായിട്ട് കോളേജിൽ നിന്ന് പഠിച്ചിറങ്ങുന്ന കുട്ടികൾക്കും അവസാനത്തെ ബാച്ചിലെ കുട്ടികൾക്കാണെങ്കിലും ഇവർക്കൊക്കെ ഉപയോഗമാകുന്ന, അവർക്ക് അവരുടെ സ്കിൽ ഡെവലപ്പ് ചെയ്യാൻ പറ്റുന്ന, അല്ലെങ്കിൽ അവർക്ക് അവരുടെ കരിയർ ഒന്നുകൂടി ബെറ്ററാക്കാൻ പറ്റുന്ന, അല്ലെങ്കിൽ പുതിയ കരിയർ തേടുന്നവർക്ക് അതിലേക്കൊരു പാത കാണിക്കാൻ പറ്റുന്ന അതിനുള്ളൊരു ഹെൽപ്പ്, അതൊക്കെയാണ് നമ്മൾ ഈ ടോക്സ് കൊണ്ട് ഉദ്ദേശിക്കുന്നത്. സോ ടുഡേ ദ സെക്കൻഡ് സെഷൻ of this wonderful program, monthly Alumni Talks, will be hosted by Arvind Venugopal. He is the engineering director with Intel Corporation in California. So let us hear the rich experience from Arvind Venugopal, who has graduated in 98 from our college, from Electrical and Electronics Department. Thank you, dears. So, ഇനി അങ്ങോട്ട് എല്ലാ മാസവും പ്ലീസ് സ്പ്രെഡ് ദിസ് ന്യൂസ് എമംഗ് യുവർ ഫ്രണ്ട്സ്. നമുക്ക് ഒന്നിച്ച് ഇതിൽ പങ്കെടുക്കാം, പുതിയ പുതിയ അറിവുകൾ നേടാം, പുതിയ പുതിയ സെഷൻസിൽ പുതിയ പുതിയ ടോപ്പിക്സിൽ നമുക്ക് ഒന്ന് കേൾക്കാം, ആസ്വദിക്കാം. കൂടുതൽ നമുക്കും ഒരു ഉപയോഗമാവും. അത് പങ്കെടുക്കുന്ന, അതിൽ സെഷൻ നടത്തുന്ന അരവിന്ദിനെ പോലെയുള്ള നമ്മുടെ അലൂമിനി മെമ്പേഴ്സിനും ഒരു വലിയൊരു എൻകറേജ്മെൻ്റ് ആവും. അവരുടെ എക്സ്പീരിയൻസ് നമുക്ക് വേണ്ടി ഷെയർ ചെയ്യുന്നു. നമുക്കതിന് അവരെ അഭിനന്ദിക്കാം. നമ്മുടെ ഇന്ന് വന്നു ചേർന്നിട്ട് എല്ലാ കൂട്ടുകാർക്കും, എല്ലാ അലൂമിനി മെമ്പേഴ്സിനും ഒന്നുകൂടി വെൽക്കം ചെയ്തുകൊണ്ട് ഐ എം ഹാൻഡിങ് ഓവർ ടു അവർ ഓൺ Arvind.
Thank you, Sunil, so much. And I want to start with a lot of. I'm indebted to the Alumni Association, Sunil, Nitin, and all the folks who have worked in the back. So first thing, I was humbled to be, asked to do this. I follow Jafar, who was the first presenter. Is a legend. And I think there are a lot of legends in our college who have started, are doing really good work. So extremely thankful and honored to be one of the speakers here. I think my journey is still going, and but I still would like to share where I am right now, and how I got there. Maybe if I can influence a few to embark on this path, that will be success for me. Okay. So let me go. One pager about me, just to tell you all the fresh grads or the people who have been recently working or still thinking about career in this area. Um, uh, can you just 1 second? Okay. ഇതിങ്ങനെ മാറിക്കൊണ്ടിരിക്കുന്നുണ്ട്. Sorry. Can everybody see this? The screen show. Otherwise, it's going without my control. I don't know why. Um, is it visible? Okay. Okay. So I'll stay in this mode. So currently, I'm a director at the Manufacturing and Product Engineering Group at Intel in Folsom, California, which is a town near to the Bay Area. So the extended Bay Area, which is the OG Silicon Valley, right? I know Bangalore is soon replacing that Silicon Valley, right? But this place is close to that. So a few things of how my career has been charted. So one thing, I'm a hardcore loyalist to the company, at least in the advent of microprocessor and the computer that came up, memory chip, phones, everything runs on chips. So I called VLSI, I picked the name VLSI, but it's a very interchangeably used, it's a very broadly used term. You can hear people say silicon industry, some people call it semiconductor industry, and I'm intending that entire chip making industry as such. So a few more points that I wanted to highlight, that there are different types of semiconductors. I know the electrical and electronics people will in the audience will be able to understand or hear have heard of these many of these terms, but others just indulge me for a bit. But the semiconductor industry, the technologies, there are many of them. Um, uh, the one that I will be talking more about is the silicon based CMOS technology, or CMOS for short, but it's CMOS FET. It's a kind of a transistor, but there are many others. You have the traditional bipolar junction BJT transistor. There are gallium arsenide and different technologies out there. But CMOS has emerged as the most cost-effective, most scalable, and perfect for digital and logic implementation, which is your microprocessor, your memory, your graphics processing unit, and so on, right? Versus it is not super perfect for RF radio chips and analog and mixed signal, but for those, usually some of the other technologies work best. But CMOS does scale, and it is cheapest. It's using silicon, which is the sand that Earth has abundantly available. Of course, that part is now getting, there is a lot of demand for sand because the entire battery making, the renewable, battery industry also needs a lot of silicon. So, but still, of all the elements that is used for making transistors, silicon is by far the most commonly available. So the CMOS, silicon based CMOS, is by far the most popular one. But within that technology, um, over the time, a flow has emerged, which seems to be the fastest and most bug-free way of doing it. It is called, standard cell-based semi-custom ASICs, right? And I'll try to briefly explain what that means. That's in the table on the flow chart on the right. But one more thing I want you to take away from this particular slide is Moore's law. I think most of you might have heard. Um, Moore was one of the pioneer of this industry and one of the founder of my company Intel. So what was an observation that he made 60 years ago, that he sees that number of transistors in a chip doubles every 2 years. Or essentially, what he said was the chip. If you have a 4 by 4 chip, 4 centimeter by 4 centimeter chip, that could do a certain job for you. It could be a CPU for a computer, or it could be the heart of your graphics card that you use for your gaming, or whatever the application might be. In 2 years, the same amount of circuitry can be packed in a half the size of that, in a 2 by 2. So that is the rapid pace at which this technology has developed. Of course, there's some breaks now, because now we are talking about billions of transistors within a chip, which also means that one transistor, um, the physical length and dimensions of a transistor is now measured in angstroms. So 10 to the power of minus 12 meters, right? So that kind of it's you're talking about atomic level, right? The gate, which is one of the bridge between the two nodes of a transistor, is now tens or hundreds of atoms. So slowly, I think we're approaching a place where the semiconductor based industry will slow down a little bit. It's still got a decade or two before it comes to a grinding halt. But by the time quantum computing and other replacement technologies will take over. But for the foreseeable future, semiconductor based, CMOS based technology is going ahead. So now quickly about the what I mean by ASIC flow. This is for folks who want to dig into this area, want to make a career here. So we need to understand that the ASIC has emerged as the IC that is oft used, mostly used, which stands for application specific integrated circuit. As the name suggests, it's very intuitive. It's built for a particular application. A CPU is a central processing unit for a computer. That's it's the application set for that chip is already predetermined. So it becomes easy to design something where you know what is expected of it to do. But even within ASICs, there are full custom ASIC where you have to hand design everything. And then you also have a completely open, programmable chip called FPGAs, which is also available. But they are not they are used, and they have custom usage models for those kind of ASICs. But the most common one, or 90% plus of the industry, the chips that you see, it falls under the semi-custom ASIC category. And even within that, there are multiple ways to do it. But I have kind of put red circles. The cell based and a standard cell based methodology is what is used in 95% of the industry. What I want to say here is, um, if you are aspiring for a job in this industry, you would see people talking about, "Hey, I build standard cell libraries," right? In working for Synopsys or Cadence or some of these companies. So they're all talking about this semi-custom standard cell-based design flow. And it is kind of, if you use this design flow, you can come out with a product every year, start to finish. That is how easy it has become. And there are industry tools to automate every step of your flow. And so this is the predominant employment giver methodology. All the others, there are small companies which does, but that's the lion's share of skill set needed. It will be in a semi-custom ASIC standard cell based flow. Okay, so enough about that. So that was a what is VLSI. So going back to the topic, why VLSI, right? I'm going to go a little bit high level here, right? So for me, this is very personally, points that I wrote down, right? From what I understand, it's a true multidisciplinary engineering skills needed industry. um, I don't want to belittle IT or computer software people. It's a fantastic industry. It's pulled the country out of poverty, to be honest. So there are a lot of people who are needed there. It's a lifesaver. But I also hear from people who are core engineers who love engineering, who say, hey, I'm only able to use, say, 10% of what I learned in engineering school in when I'm doing my software job. Or or it's a very monotonous, very one-dimensional job. Now, this one, for all those people who crave to do engineering, innovative engineering work, very challenging, this is definitely one option. And it needs multiple domains of engineering. It's not just electronics or computer architecture or like three courses. No, there are multiple skill set needed. So you actually start appreciating what you learned. People might tell that the syllabus is archaic, it's old, it needs to be updated. Yes, but I still look back at many courses that I did in my 4 years of engineering at undergrad and my bachelor's, and many of the skills that I learned there has been very useful. And so it's a core engineering area. That's one, right? Um, and it's constantly changing. The it's riding a wave, like Moore said. Every 2 year things are changing. So it's always there's new challenges, very technically challenging, very high reward for creativity and skill. And let me go a little bit about business side, right? So this is expected to grow. It's a $575 billion industry in 22. It's going to be 1.5 trillion in 6 years, 7 years, and growing at a growth rate of 12%. No, so that is a huge market. And now everything runs on semiconductors, right? You name it: vehicles, appliances, your microwave, your fridge, your car. A car has 38 microprocessors and numerous other ICs. And so you might have heard about supply chain problems during COVID. It was predominantly because of supply chain issues in the semiconductor industry. The chip industry slowed down because of issues, and that kind of caused a lot of problems everywhere, right? And so much so that you can call semiconductors the new oil. It's not even now, but it's been the fact for past 5-10 years now. So countries are waging chip wars, right? They're trying to secure this know-how and not be dependent on one, global power versus other. In fact, the Indian alliance, it's a geopolitical alliance that India has with Japan, Australia, and US. And silicon making is one of the primary things. So with all that, US government is last year, in order to become self-reliant or not be over-reliant on a few countries, they're incentivizing businesses to come and invest even $50 billion worth of investment. Indian government has announced 10 billion worth of investments, and the number of companies that are lining up to start shop manufacturing semiconductor in India is just exploding. Only in last 3 months, 2 months, Micron and AMD has announced, right? And that's just two. There are multiple others in the pipeline, right? I have one more slide about that part, but I want to also talk about, there are two business models. Again, I want to kind of talk a little bit about high level, the business strategy, right, aspect. So Intel and Samsung and some of the semiconductor fabrication companies, they have a vertically integrated model, right? What you call a upputhattu karpuram vire kind of thing. So they do everything. Whereas the rest of the world has moved to a fabless model where they delegate, they subcontract the part of semiconductor fabrication to companies which are specialized in that: TSMC, UMC, and many others like that. They all that those companies do is build you semiconductor chips and wafers and send back to you. But in this model, most of the other companies, which is in US and India, um, all they have to do is specialize in designing well. And if they follow the semi-custom ASIC standard cell-based approach, they can design a chip from start to finish in 6 months. Send the design files to TSMC or this fabulous you know custom foundries or fabrication plants, they will send you back working silicon in 3 months, 2 months, 3 months, and you take the rest of the time to test it, make sure it's qualified, and you should ready to ship in 1 year. So so many more companies are getting into this bandwagon of making their own chips. Apple has been extremely successful. Just they started 7 8 years ago with their or maybe 10 years ago with their microprocessor for their phones. Now they're making their own microprocessor for their laptops as well, the M1 and A1 series. But we know Google is jumping into it, investing billions into it. Microsoft, Meta, they're all started designing chips, which means good for engineers like us when we're searching for jobs, and that means there are a lot more options. Okay, so this probably is a little bit oh, that's too much. So I just wanted to show you maybe what are the top semiconductor companies, right? This is too much. Sorry for an eye chart here, but if you can strain and see. So on the left hand side, I listed down the global companies, which semiconductor companies, which made more money in the first quarter of year 23. So my company Intel has made 12 billion, but you also you should notice that it lost 17% year over year, right? So it's on a slightly downward spree. That goes for Samsung, but rest of the companies, some have gone down, but many others are just booming. Likes of Nvidia, AMD had a minor setback, but they're back on like big recovery. And many other companies, most of the others are the fabulous semiconductors company, right? Broadcom is doing really well. And what is I want to mention that I think all of these have a presence in India, right? And this does not include the foundry companies like TSMC and UMC. By sheer revenue, they would find place in the top 10 easily. But other than those companies, all of these are in India. They have their design houses in India and so on. But what's also very heartening to note is the lot of homegrown companies which are doing really, really well. I can send the slide deck so you can actually see the numbers. You can see how much money they have made, or the market cap. So very common names: HCL, Vedanta, Tata is there, and many others, right? NXP is doing really well. But NXP is, I think, is a global company, but these are the Indian companies. So there is a huge potential in India, right? Both from global companies setting shop or expanding in India. Intel, for example, we have 12,000 or so employees, and we have in Bangalore, and then the state-of-the-art facility. That's it's brilliant, right? Um, Other than it'll be tough to just get there, right? Navigating the traffic, but it's a huge campus and growing. Okay, so with that, let me dig back into the ASIC flow that I was talking about, right? The design flow. This might be a little bit academic, but if you indulge me again. So the first step in our this semi-custom ASIC design flow is more qualitative work. You're trying to understand what the customer wants, and you design a product. This goes for any product. You can be a software, you can make a soap, but the first step is invariably this: you're trying to find what should be the next product out, what should be the specifications, what do the customers want. um, but in as it pertains to chip making, we are deciding main things like, hey, what should be the power consumption, what should be the performance, performance per watt. Performance is measured in clock speeds, how fast things operate, and how big the chip should be, right? Those are the bounding box for us, right? Power is extremely important, because if you're making a chip for the phone, you want the phone to, and the CPU is the biggest power consumer in your phone. You want your phone to last, battery to last an entire day or two, right? And it all boils down to how well the chips are designed. If they are designed badly, they just drain the power very quickly. So next is, when next step is probably the most intensive design work that needs to happen. This entire flow, there is it has been automated over the years by, there are companies like Cadence and Synopsys. They have made these softwares called engineering design automation tools, EDA. So what it can do, those you if you go ahead at architectural design and you write code in a behavioral language, it's a very English like language. You're just telling what you want it to do. You don't have, you may not have much knowledge about transistors or circuitry or core VLSI electronic stuff. But if you can write code like C, right, a behavioral code, mostly dealing with Boolean algebra, right, your ones and zeros, the kind of code that I show in the box on the right. Again, it's a little hazy picture, but if you can write a code like that, then you can just give it to a software which will convert it from one step to another step to another step, and then your work is done pretty much. So it's all fully automated, right? So all you have to do is make sure that the code that you write, the behavioral code you write in the step two, is good, it's bug free, and so on, right? But it goes through many steps from there. It converts from that to a transistor level, right? Sorry, a gate level, like shown in the third box, from gate to a transistor level. And in the end of these three boxes, in the first or three stages, you get a picture like the black rectangle you see on the right. That is how that is the layout of all the circuitry, the pieces that has to be etched and designed in on a piece of silicon, right? And like I said, all of that will be generated by a tool. All you need is human intervention to make sure that every intermediate step, bugs have not been inserted, and you test it and validate it, make sure that every step is happening properly. But the EDA software automation tools handle, and they take you all the way to this uh, file, which is basically a what they call it, a GDS file, or the layout files. So your job is pretty much done if you're a fabless company. You get these files, and so this is a top view. So you what you need to understand is there is, I don't know, 25 different layers of silicon stack up, and circuitry is drawn on each of these layers, um, and that together, that stack up of 20, 30 layers of silicon, together makes a chip, right? Um, and these design files, you send it to this company in Taiwan called TSMC, right? And that's the factory, that picture that I put. That is not a true blue factory. It's a floor where they take this design and send you back wafers that is on the picture too, or they package and send you a chip that you see when you open your computer or your phone. You can see a chip there. So they send you something back like that, and they are perfected that art. So it's it's very high quality. And then once you get it back, your job is to take it to a lab on step number 5, and do validate it, make sure it's bug free. You test it for high volume manufacturing. You qualify the product, much like how you qualify any product, right? Whatever product you are making, you have to do qualification steps. um, and then you work with your customers. For somebody like Intel, we work with Microsoft and Dell and HP, and any customers, even HCL and other computer makers, right? And make sure that they don't have it work seamlessly in the new laptop or desktop that they're working, right, or new server that they're working. And once we have vetted it and it looks golden, Then we turn on our factory, which will handle the automated testing and shipping. Okay, so this is the different steps. I know I have only 15 minutes, so but I have two more slides. So I think I can go a little bit deeper. But this is again the same steps that I mentioned the previous slide. That's the column number one, ASIC flow step. But I would try to throw in what skills are needed. Right, it's probably too much to absorb right now. But if I can send it to all of you, and if you can, and so this is what my understanding. I didn't steal it from web, so take it with a grain. But if you step through the different stages, each of the stages you need multiple job types, and people can. So let me just take an example, right? The first one is a product specification. Okay, that let me skip that. So if you look for RTL coding and functional verification, which is step number 3 in the flow that I drew, right? You need somebody called front end design engineers. There are people who start their job as front end design engineers, and they can become senior VPs and senior VPs and design managers and retire. That's a job code in itself. But and then you'll need embedded software engineers in the same phase of the project. And I've also thrown in what skills might be required when you're in your bachelor's, or when you're venture if you're planning to do a post graduation. So you need to be thorough in digital electronics. You need to learn RTL coding, the ASIC design flow. If you want to be embedded software engineer, of course, you have to specialize in embedded software writing. Similarly, if you keep going down, so the fabrication at foundry, which is 1, 2, 3, 4, almost step number 10, right? So that is like I mentioned, it's a factory that is currently in Asia mostly. But in order to set up a factory of that size, one factory takes $6 billion to $8 billion of investment. So it's a huge, and like that, you need hundreds of factories, right? So you need industrial people, you need mechanical to run a factory, like it could be like car manufacturing, right? So it's a very multi disciplinary skills needed. You need data scientists to analyze manufacturing data and monitor it. You need civil engineers to build this very niche industry. You cannot have vibrations, for example. So the floors are shock proof, and the ventilation system and the AC system has to have zero dust. Because when you're working in a semiconductor, you might have seen people wear this funny PPE kit kind of bunny suits, right? The fact is, you cannot, and before entering these facilities, they have to be completely sanitized. Without They cannot have, forget hair, they cannot have a single speck of dust. Because if one dust particle goes on the reticle, then you can come out with millions of units with a defect. So all that needs a very specialized civil and building skills. Then semiconductor process engineering, quality engineering. So, and the skills needed, of course, various skills are needed. But each of the not I'm not intending to say that one person needs to know all of this. No, each step needs, I don't know, 50 different kinds of people, job codes, and each of them, you can make a career, start and end your career in that, right? That specialization. So it's a so if you can see, it's already, I just highlighted the important ones. But it's a vast industry and scope for one and all, right? um, so just maybe 1 minute on that, right? So my specialization is in the manufacturing testing, right? Let me see. This is where I started, and I ventured to these three areas, which all happens post silicon, right? um, all this is happening in a you're still on a computer, you're designing, you're writing a code, there is no chip, there's no real circuitry that's in your hands. This is all done in a cube or in your home, right? You can work from home, you can work from your garage, and do this, right? And this step is where all of that design is converted into chips, and it is packaged into this epoxy package, which sits on boards and computers and everything. But all of these steps, following these 4 steps, are what we call post silicon engineering. So all my career, I've just 22 years, I have just been in these 4 areas. And even here, I'm probably guilty of switching too many times, right? um, and even though I have a high level knowledge of what happens in the other areas, I never really have to venture into those areas. This is more than enough for me to become a principal engineer and a fellow. It's just the senior most engineering post in the company, or I can become a vice president, president, and go executive C-suite leadership if I have to. So you can pick your swim lane, your specialization, whatever uh, fancies you, and then you can be a specialist there. See, I mean, there's data science. You can There's a whole bunch of data scientists who are being used, even though it's a hardware making company. You would think, why do you need so many data scientists? Now, every piece of when we ship, we are making millions of units every week and shipping to customers. So, and every unit is getting tested for hours, and by thousands of tests. Each of those tests are getting their the results are getting logged into databases. It's filling up very fast. So if you have somebody who's adept at machine learning or AI, they can extract from this data um, and tell interesting trends, right? They can say all your dies on the edge of your wafer, based on the location, are coming to be faulty. So something is going wrong, and they can come and fix issues like that. So all kinds of skill sets are required, is basically what I'm trying to say here, right? So with that, maybe I'll just go to the last slide. So key takeaways, right? What I want you guys to walk away from. I know many are industry veterans here, but I'm hoping there are people who are either starting out in their career or a few years into this career. Like I mentioned before, VLSI slash ASIC slash the semiconductor industry is a very challenging, and it's one of the core engineering areas, right? You will never complain that I don't have challenging work. It's going to be tough, right? But it's very rewarding. It will satisfy all your engineering ego, right? And in the thirst for innovation and making some changes. And it's a multidisciplinary, like I said multiple times, right? So when I was writing this and I was talking to Jafar about how to construct the speech, whom to address to, right? And I was thinking about my own apprehensions when I was in college. When will I use this knowledge? Is it really needed? Kind of question. So I just wanted to answer that, right? So the engineering mathematics that we were thoroughly, trained in, the differential equations, the integral differential equations, the matrix operations that we studied for a semester, and the transformations, the Z and L and Fourier and all of that was heavily used in my post graduation, right? When I was doing my masters, when I was doing microwave radio antenna design, all of this math was like prerequisite, right? And if you ever mention to digital signal processing, wireless communication industry, and this is not even core chip design, right? All of that will need uh, you know grounding in this engineering mathematics. Even stuff like board design, signal integrity design, all of them are use Maxwell's equations, which is a integral differential equation. You need to know how to solve those. And there was other subjects where we did regressions, right? your Monte Carlo simulations, your statistics, probability, all of them are going to come back. Okay, you cannot run away from them, right? They are heavily engineering, math, and it's used no matter which field you go. Okay, and one thing, for example, even though I did electrical, one of the basic foundational courses in our syllabus was the electrical circuit theory, right? ECT 1 and 2. But what happens in an electrical circuit at a macro level goes downsized to, oh, sorry about that. I think I have only 5 more minutes left. My system is crashing or rebooting, so I'll try to finish that. So the electrical circuit theory is a foundation for even all the things that happens in electronics or in a micro level in a chip. Thermodynamics, uh, right? I didn't realize that I'll ever be using thermodynamics, but um, the some of the chip, the last chip that I worked on, it was a GPU for supercomputer. One chip, the thermal distortion power, or the amount of heat that it generated, was 450 watts. So if there was no cooling solution, if you keep your hands on it, it'll burn. It'll burn through your entire skin and muscle and everything. It becomes that hot. So we need very, very complicated water cooled. Thankfully, we don't need cryogenically cooled solutions or anything like that. But we invariably, to cool the parts, we use liquid nitrogen for certain testing things, and we have to design very intricate water cooled uh, thermal systems to keep the temperature down. So then if you have a really good understanding about thermodynamics principles and thermal design, it comes in handy. Now, of course, the electronics, all those courses are kind of, you need to be really good at the analog and digital electronics, computer architecture, microprocessor, electronics 1 2, all of that are prerequisites for core VLSI, right? So get cozy with that. um, a post graduation might help you specialize in this field, but I wouldn't think it's mandatory. I think maybe 60% of the workforce at my company is just bachelors. So they came on job and they learned and trained up. So it's not rocket science. But a post graduation will open the doors and you can specialize. And for me, it did help in multiple ways. What I've been conspicuously missing in my entire narrative was the requirement of software skills. It cannot be understated. Even though it's not you're not a core software programmer, there are many jobs within the thing where you need really really strong programmers. But forgetting about those job codes, even the regular designer, test, semiconductor have to be really good at decent amount of coding. For me, I find the C coding that I did right after college was very important. Scripting using Python and Perl, the database stuff, right? SQL, all that was very helpful. And there are a lot of other job categories, right, that I didn't even mention, right? The people management, project management, legal, HR planners. So it's a kind of a one-stop shop for all kinds of job skills and codes, and you can, you know, develop into blossom into different areas wherever your passions lie. Okay, so that was my last bullet. With that, I kind of conclude my talk today. Hopefully, even if one person is swayed and I could pique their interest in this area, I would feel very, very humbled and happy that my job is done. So, Sunil, Jitin, any last?
Sir.
Yes.
Yes, yes. Actually, that is a wonderful session. So many people are clapping and all. We can see in the slides actually.
Okay.
Actually, I am a triple A graduate also. Hearing it for long, it is much obliged for me. And actually, I think the session will be ending in some minutes. I hope there are so many doubts and all, I think, but I don't know whether we can conclude in this session. So I
Yeah.
request you to have one more session for this, for a doubt clearance or like that. if you are really interested, we can arrange one also, because people, I think they are raising hands and all. So I don't know whether it will be finishing in a minutes, because the Google Meet, actually it is for 1 hour actually.
Yeah, very
So
sorry. I didn't give time for Q&A, but I'm
yeah,
very,
yeah, yeah.
very open to setting up another time. Very happy to do that.
Yeah,
So
because actually, even I have also some doubts also.
okay, okay, sure.
I think we should meet again because we have already got some 40 plus 50 plus regular listeners in this meeting. That's a great thing for our event. So I thank each and every participant who attended the meeting and sharing your thoughts for this. Sir, I request you to talk. You continue your talk, and I thank as a part of the alumni. If the session ends, I think soon we can start our. I think we can arrange a session, one more talk or a doubt clearance session for this topic. If you are very really willing, we can arrange that. Okay.
Very, very,
Okay,
very
sir.
happy, and I can send this slide deck and my contact information to you, Jitin, so
Yeah,
we can
okay.
send it to our.
Actually, we have started a YouTube channel. No, the recording has been done, so the people can view in the YouTube channel also. After that, listening, we should must need a session also, sir.
Sure, definitely. Very, very happy to do that.
Okay. If
Jitin,
anybody have some doubts, you can ask, or else we can end the session. Okay. Thank you.
Jitin, I think we need the second session.
Yeah. Yes. Yes. That was a
Sure,
very
sure.
interesting session. That's why. That's why. That's
And
why.
it was very interesting, and
Yes. Yes. Very
we need
handy.
the second session. We need to have the Q&A session also. Next
Sure,
session.
sure. Yeah, no, no,
Yeah.
no problem at all. I'm very happy to
Yeah.
help in any way. Thanks a lot. Thanks a lot for coming and hearing me. Hope
Hi,
I didn't bore
Arvind.
you. Yeah,